Thanks for joining the webinar today. We're about to get started here. This webinar is the fourth in our monthly New Eagle webinars, and we're going to be talking about telematics. Okay, so the telematics that we'll be talking about today is part of our Raptor platform, and the reason that we're offering it is to make it part of the platform to interoperate with the rest of the tools and components that we have. So the platform is a set of tools, components, and processes that we've designed to work together, and the idea is to enable you to rapidly develop production controls for today's advanced machines. And with a complete platform, I'll show you the range of tools and when during the system lifecycle that you use them. The idea of a platform is that we can take advantage by designing things to work together. We can take advantage of the different strengths that each component has and allow data to flow between the tools and components more easily. And we call this an intelligent machine. So the platform has tools and processes and components for each phase of the system lifecycle. So from start to finish, kind of concept, design, validate, all the way through fielding the application and servicing it. With the concept and development, we talk about rapid prototyping here and using the model-based tools to do modeling of the system and simulation, and then those same tools are used to do code generation. We have tools for validation, tools that you'll use at the end of line, and today's topic, fleet management and data logging via our telematics solution. So the various tools that we have as part of the Raptor platform here, we have for the concept and design phase, we have Raptor and Modohawk, and those work with MATLAB Simulink tools to allow you to do your modeling simulation and then via code generation to actually create the embedded software that runs in the different ECUs and displays. We have coming out at the end of the year, Merlin, which is a calibration tool for the Raptor ECUs, and Mototune's used with Modohawk ECUs. It's also used, in addition to calibration, each of these has a service interface, and that allows, it's a lower function set of capabilities in the calibration tool that allow the system to be serviced, things like clearing faults, looking at active faults, and updating software as new software versions or patches are released. We have a set of data loggers, part of what we call testimony presently, and that is a set of data loggers, either both PC and embedded data loggers that can collect CAN data from the system, and there's associated tools for analyzing that data. The validation phase of the system lifecycle is accomplished with our New Eagle automated testing tool, what we call NEAT. That allows you to work with both Modohawk and Raptor ECUs to do regression scripts, and you can kind of do a simulation on the bench and create test scripts that run run in an automated fashion against your controls logic. That tool can also be used at the end of line to do reflash of the controllers and configuration of end-of-line calibrations like a VIN number or other things that you might want to do to configure a vehicle as it's leaving a production facility. And that can also generate a kind of like a vehicle manifest or a PDF that describes the software versions, serial numbers, VIN numbers as the vehicle leaves the production line. And then today's topic, telematics. This tool can be used during several of the phases of development and system lifecycle. It can be used as a remote engineering data collection tool, so collecting data as the vehicles are used in like a limited fleet test. But as you actually field the system, it can be used to do fleet management, and we'll talk about each of these today. So I wanted to kind of frame where telematics fits. On the opening slide here, we had kind of this high-level overview of the Raptor platform that describes that it is a set of tools and products that work with our systems. Telematics is a feature within the platform that works with all the ECUs and displays and networked components to allow you to do remote management, diagnostics, and software updates, calibration updates of the components within the platform. You can get telematics from other places, but the telematics that we're offering, the reason that we offer it as part of the platform is we can provide an integrated feel for the telematics with features like remote reflash and calibration that's difficult to do with a third-party non-integrated telematics offering. So with that, I'm going to turn it over to Scott to talk in more detail about our telematics.
Thanks, Ben. My name is Scott Favor. I'm a senior software engineer here at New Eagle, and I've been working on the telematics platform for about 1.5 years now, and it's what I'm here to talk about today. So, first of all, before I start talking about engineering and logistical challenges, what is telematics? Telematics is basically enabling remote monitoring of vehicles or in-place equipment through cellular data technology. So basically you're plugging a cell phone into the vehicle or into the oil rig or whatever it is that is far away from your engineers to enable them to have visibility as to what is going on. So there are several reasons that we do this, and I'm going to touch on them briefly here. First, you can collect data during fleet and beta testing. So this is during the engineering process. The vehicles are still in development, and maybe there's some calibration work that needs to be done, or maybe there's some problems with the harness design, or any number of other things that can be difficult to diagnose with either on a bench or with a vehicle sitting in a garage that happen when the vehicle's out on the road or on the job site or in operation. So this enables us to collect data while a vehicle is in operation to enable engineering to tweak performance and diagnose system problems. Once you're in production, though, there's a slightly different use for remote data, and that is monitoring vehicle health and performance. So you can keep track of see vehicles, say their hours and odometer, and see if certain vehicles are running hot or having trouble keeping a charge if they're electric vehicles. You can do that sort of diagnostics remotely and hopefully have a preemptive maintenance strategy that allows you to take care of the equipment before you lose the ability to use the vehicle in the field because it goes down. If you have road vehicles, you can also track their location, make sure they are where they are supposed to be. And one thing you could do with that is do some route analysis to see if there's some efficiencies that could be gained through reduced fuel consumption. But all of those aside, one of the most exciting things we can do is we can push software and calibration updates to vehicles in the field. And that means that you don't have to wait until vehicles get back to a certified garage before you can push a critical update out to them. You can do it while they're in the field. So in terms of vehicle monitoring, we've got a couple of sort of high-level features. Most important from an engineering standpoint is CAN logging, which is configured via a DBC file. That is a passive logging, so it just sits and listens on the CAN bus for any signals that are broadcast by any module on the bus. And we then collect that data and periodically transmit it to a server where it is made available for consumption either by the engineers or for fleet management purposes. In addition to CAN logging, each TCM, Telematics Control Module, has a GPS tracker on it. That's a GPS antenna that just lets us keep track of where a vehicle is, latitude, longitude, altitude, and so you can know where the vehicles are out in the broad world. In terms of fleet monitoring, we can use the data logged via CAN to schedule maintenance. So when a vehicle reports that it's approaching a maintenance threshold in terms of hours or miles, you can get an alert saying, okay, this vehicle needs to be needs to get its oil changed, needs its belts changed, needs its transmission flushed, whatever you need to do. We also have geofencing available. Geofencing is basically, if you look at this picture on the top right here, you establish an area on a map that the vehicle will be moving in or out of, and you can get alerts set up when a vehicle crosses that threshold, crosses that boundary. That's mainly used for work vehicles that are assigned to a specific job site, so you can tell if somebody is going and joyriding on your dump truck, for instance, going for a pizza run.
Another case of geofencing is to track fuel usage inside of a certain geographical region. So you can understand when the vehicle's in there and monitor, if there's fuel being used within that region.
Another thing that we can do is we can set up alerts. So if there are thresholds for operating parameters like RPM or coolant temp or whatever is appropriate for your application, that indicates that a vehicle is either malfunctioning or being used in excess of its rated capacity, you can get an alert indicating that so that somebody who needs to can go see what's going on with that vehicle. In the fleet monitoring system, we also have a 3-tier account hierarchy because obviously you, as the OEM, you're not necessarily going to be using the vehicles directly. You're going to be selling them to people who will use the vehicles. So the 3-tier account hierarchy lets you manage all of the vehicles and look at everything. The distributors can only see the vehicles that they have sold or have in stock, and the end users obviously can only see vehicles that have been sold directly to them. This is just a screenshot of the fleet monitoring website. You can see it's got a GPS map with the current location indicated, and it's got some graphs and tables for just sort of a hierarchy, or sorry, an overview of what's currently going on with the vehicle, how it's been used in the last 7 days or so. So this is not something that would be useful to an engineering team necessarily, but this is something useful to somebody who's running a work site and wants to make sure that all of the vehicles are performing correctly.
A couple other points on the fleet monitoring interface. These are often going to be, there'll be some specific features that are desired by a particular customer, and so oftentimes there's some customization that needs to take place on the fleet monitoring side to get the right interface. we work with a lot of different types of vehicles, electric vehicles, hybrid, multi-fuel. So they have different things that want to be monitored. For instance, an electric vehicle, you may want to monitor the power usage, kilowatt hours per mile, or miles per kilowatt hour, and that wouldn't really be applicable to a say a diesel engine application. So we're able to do customization on a per project basis, basically, I'd say.
Okay, so now I'm going to show you a demo of our engineering data logging. This is a feature that we are in the process of developing, so this is a prototype. This is not the finished product, but it's in a state where I can show you what's going on. So the idea here is we have a model running on an ECU that we want to log some data out of. So this is the model. This is a Raptor model running on one of the Raptor ECUs. It's very, very straightforward. All it does is it broadcasts one CAN message with some fake data. You can see we're generating some sine waves and then just plugging them into the message here. And you can see we've got 4 signals: engine speed, coolant temp, requested torque, and actual torque. This model is currently running on one of the Raptor ECUs that's sitting next to me on the desk. And you can see this is the CAN traffic. I'm plugged into the CAN bus via capacitor CAN adapter. And this signal CAN ID 1 is that message being broadcast. Every once in a while you'll see this other message going by, 19FOFF, etc. And that's just a message that's broadcast every 5 seconds by the telematics unit, and that indicates that the telematics unit is up and running and says something about the GPS signal and the cell signal it's getting, and also gives some progress if we were doing an ECU reflash, which we are not going to do today, but that's going by.
So what you're saying is that message, the 19F0FF4A, may be useful for other modules in the system to monitor, to know details about the telematics. Can you show how you set up that CAN message in the model?
Yeah. And to answer your first question, yes, the intent of that message, the 19FOFF4A, is to be used by a display so that you can show the user if an update is in progress or whatever your display needs may be. So to set up this is in Raptor is really pretty straightforward. You have this CAN transmit message block. You select a DBC file, and this is the DBC file we're using. You can see it's got just the one message, and that message has 4 signals: actual torque, requested torque, coolant temp, and engine speed. Okay, each of those are a 16-bit value being broadcast every 100 milliseconds. Okay, and each of these signals generates an input port on the block, and then we can just feed the value in. And this particular message is set to transmit every 100 milliseconds, so it'll use whatever value it has when it gets transmitted. So that all being said, let's go to the portal here. Let's refresh that. So this is because it's a demo, of course, things are not working exactly as I'd hoped, and it currently says that it's out in the middle of the Atlantic instead of in Michigan, where it should be. Here we go. That's in Michigan. And you can see this is our new office. It's so new, in fact, that it doesn't say New Eagle yet. It still says the old owner of the building. But you can see down here, we've got, over here, we've got some just basic info about the vehicle. We've got a VIN, which I haven't filled out here because it's sitting on my desk. a couple of identifiers, and a phone number for the TCM, because it is in fact hooked up to the solid data network. And some custom functionality we might have in the future would be sending text messages, or the hardware is actually capable of acting as a phone. So you can set a couple of the inputs and outputs to be a microphone and a speaker. So here on the engineering data tab, we've got some data, and Ben has a comment.
So the kit, the telematics unit that we're looking at right now, that is on the bench on your desk here with, and it's connected to the module running the model that we just took a look at, right? Okay.
Yes. So I've got a C4MAX, which is the name of the hardware, hooked up to a Parker ECU on the CAN bus with my laptop. This, however, is going, the data here we're seeing is going out over the air. It's going to a server that's running in the cloud that's hosting the stuff that we need to run to collect the data. So let's get some data here. You can see we can pick the start and end date, and I'm just going to download it, see what it looks like. Okay, so we've got a CSV file here, and you can see we've got a timestamp on the left here that's in universal time. So if you want it in a specific time zone, there's some Excel magic you can do to translate that. Then we've got two signals, coolant temp and engine speed. And we can do this. You can see it's we've got those nice sine waves being generated by the model. So that's all well and good, but what if one of the engineers working on this sees a problem, or the driver reports a problem, and the data that we're logging isn't quite enough? Well, what we can do then is we can change what's being logged. So
before you do that, what is running on the device right now? What's running on the telematics unit?
So running on the telematics unit right now is this file, engine info 1, which you can see only has two signals, coolant temp and engine speed, which we just saw in Excel. And what I want is I want to see the torque values as well, actual torque and requested torque. So what we're going to do is we're going to upload a DBC file that contains all of the signals that we want to log, and only the signals we want to log. The telematics unit will log everything in the DBC file. So for instance, you don't want to upload the entire J1939 DBC. That would get you a little bit more data than is probably useful. So we're going to do 2, and we're going to hit upload. Okay, now an update is now available, and you can see here this update is available. This is a list of all the updates, the update history for this TCM, and you can see it's got quite a bit because this is one of the test devices I've been using. So normally that's going to go and check in every hour or so, but I don't want to make you guys sit here for an hour, so I'm just going to poke the device, and that's going to take a little bit of time because it's got to log in, download the update, apply it. So while that is happening,
so this update is configuring the messages that the telematics unit is going to send to the back-end server, right? It's not updating the software in the telematics unit or the software in the Raptor ECU.
Correct. This update is strictly the configuration for data logging. All it has is the info that the telematics unit needs to change its CAN logging configuration. We can also update, and we're not going to show this obviously right here, but we can update the software running on the TCU, and we can update settings on that, and we can also push a reflash of any of the Raptor modules sitting on the bus. So while that's going, let's talk, and that's going to take a few minutes, so we'll just let that run while we continue here. So speaking of remote update and reflash, this is, as I said before, what we're really excited to offer. This is a real value proposition for our customers. Basically, we can reflash selected ECUs right now. We support several, and we have implemented right now several of the Motohawk ECUs, including the 112 pin, the 70 pin, and the 48 pin. We have planned to support all Raptor Platform ECUs, and that slight caveat on that, that is just the modules that support update over CAN. So things like our displays, the vCAN displays, you update by sticking a USB stick in the back. Obviously, we can't do that remotely, but the ECUs are planned. Excuse me. So since we're talking about sending a reflash over the air, that means that the telematics unit is going to be downloading an SR file for the Motohawk modules and then sending that over the CAN bus. It is, a slight concern that these files are being transmitted in an automated fashion. There are, obviously our customers have quite a bit of investment in the software and the calibrations that are being moved about. So in order to provide some security for that, as soon as a file is uploaded, it is encrypted using a 2048-bit private key, and the files are stored and transmitted in an encrypted format, and they're only decrypted once the TCU is ready to apply the update. So even when it's cached on the TCU caches it in an encrypted form to make it as difficult as possible for somebody to intercept that and possibly compromise your IP. In terms of safety, the ECU and the TCU have a handshake to ensure that the update is being applied to the proper device. And a part of that is the Safe to Update protocol, which is a CAN-based protocol.
So before we get into the Safe to Update too much, remember that when we're reflashing the ECU, the ECU's application is not running. So in the normal system operation, right, the ECU is in control, supervising, or actually physically controlling a mechanical or mechatronic system. So it's in control of potentially dangerous actuators. And so we need to be very careful about when an update is applied, because the control application will not be running at that time. So what Scott's going to describe is the Safe to Update protocol, which is a piece that goes both in the embedded side and in the telematics unit that assures that it's safe to update. So before I give it back to Scott, I want to make sure that if there's any questions as you're going through this, there's a question panel on the GoToWebinar, and if you put your questions there, we'll have time at the end to answer them, and I'll be monitoring them, and if they come up and they're topical, we can answer them during the actual topics. So that should be available in your GoToWebinar panel there.
Thanks, Ben. Okay, so safety is paramount, of course. We're talking about a reflash of a vehicle out in the field. That vehicle may be doing what it's supposed to be doing, so driving on the road, lifting heavy things, doing whatever. And obviously we don't want to initiate a reflash while it is in the middle of doing something dangerous to either the mechanisms or the people in or around the vehicle. You don't want to do a reflash while a bus is, doing 70 across a interstate bridge, or parked on a railroad tracks or anything like that. So basically what it comes down to is the ECU has to determine when an update is allowed based on what it is currently doing. As a for instance, one of our existing projects is an electric bus, and the very simple determination is that they don't do a reflash unless it's plugged into the charger, because then they're relatively certain that nobody is going to be trying to start the bus right away. And that brings up an interesting point. As Ben said, this is earlier, we have a wide variety of applications being created by our customers. Some are electric, some are hybrid, some are straight diesel, some are other that don't fall into those easy categories. So determining when it's safe is very application specific, and it needs to be part of the ECU software design from as early an age as an early a point as possible. So adding this to an existing model may be more challenging than if you design it from the start with this in mind. In order to facilitate that, we provide a simple Simulink library for handling the CAN protocol between the TCU and the ECU. It's just a couple of blocks, one to notify the application that an update is available, and another one that notifies the TCU that the module has decided that it is safe to update. Okay. And I'll just talk about system architecture very briefly before we go back and see if our data logging has logged anything useful. So you have multiple vehicles in the field. Each of them has a module or more than one module and a telematics unit that talk to each other over the CAN bus. The telematics units communicate over 3G GSM cellular connection to a server sitting in the cloud, and that pumps data into and out of a database which we can access via a web portal. And I'm going to go back to that web portal here in a moment, right here, and let's see if that update has gone through. And you can see that this one that we just started is complete, and that we have data as of a minute ago. So let us see what it has captured. Open up the CSV in Excel. As you can see, because I'm still getting the data from earlier in the day that didn't have the torque values, that for the first several dozen rows, we don't have any values for torque. But if we go down to the end here, as soon as we start seeing that, and you can then we have torque values. So let's throw this into a graph. And you can see here, right about here is where the update occurred. So there's a slight disruption in the signals because I'm not actually graphing against the time values, just the index in the spreadsheet. But you can see we're starting to get the torque values here. So the engineers can then go through and figure out what's going on, and hopefully the new values they requested will show what is happening. Okay, so we've got a question here. Let's see if I can actually read that. What is the maximum sampling frequency for data logging? And what is the latency between an event occurring on the ECU and being visible on the telematics system? So the maximum sampling rate that the TCU supports is 1 second. So this is not going to be a super high frequency 50 millisecond data logging. And we are hoping to support 1 second frequency on the server side. That is, and we've been able to do that. So as a reminder, this is a prototype, so it's not quite finished yet. As for the latency between an event occurring on the ECU and being visible in the web portal, it depends entirely on whether or not you have currently have a cell signal. So if the vehicle's in a place, like it's in a tunnel or it's in a place with poor service, it may have to wait until that vehicle gets back into a service area before we see it show up. But barring a situation like that, it should show up as soon as the TCU sends the data through. So probably less than a minute.
So another thing to point out with related to that question is what we're showing right now is really an engineering interface. So this is used to, if you think about maybe like a 10 fleet trial when you're at the end of your validation phase, you've got like a fleet testing before you go to final production. You're collecting data on vehicles that are kind of in use or being tested. So this interface allows you to go and collect the log. In the fleet management portion, you can actually schedule alerts to occur. So if a fault were to come up, you could have an alert happen, and so that would give you kind of maybe more timely. Here, you're going after the fact and collecting the log, but you do get a spreadsheet that you can analyze with all of the data. And when you saw the spreadsheet that Scott pulled earlier, we had in the initial the beginning of this demo, we had 2 signals configured for the unit for the telematics unit to collect. We switched over to have 4 signals, and you saw in the Excel sheet that there is a period of time during today that we collected the data for today as the CSV log. Part of the log only had 2 signals, and then at some point those 4 signals showed up. If we were to send in another update with 6 signals or 5 or whatever, those would then show up later on in the log. And so this interface is really an engineering kind of data-centric view of things. When you go into a fleet scenario, you're going to have kind of more meta type data, kind of higher level, but then if an event occurs, you can have kind of a snapshot or a more in-depth view of a scenario.
Okay, we've got a second question here. Can the telematics DBC file be state-based? They've given an example with our application. We have driving, stationary, operation, a couple other states. During each state, we would need different signals recorded at different sample rates. So the answer is no, not really, kind of, sort of, yes. The way we would do that would be you would broadcast a signal indicating what state it's in, and then we would log everything for all of the states. And when you're analyzing it, you could then see, based on what the current state is, which values are important. It's not necessarily the most efficient way in terms of data, which is a concern with all of this, of course. All the data is being broadcast over the cell network. So the more data you broadcast, the more frequently, the higher your data charges are going to be. But that is how we would address that right now. If we needed something more sophisticated, actually switching between multiple configurations based on a state, that would be a sort of custom application that we would need to work on for that specific application.
And another thing to point out is this is configured via a DBC file. So what you put in your DBC file is what gets collected. Maybe Scott could talk about if there's any limitations. He did mention you wouldn't want to put, for instance, the whole big J1939 DBC that actually is, I think, like 1,000 messages or something. But is there a practical limit that you know about as far as number of messages and signals?
There's no hard cap, but it basically comes down to how much information is useful and how much information is just going to be not useful, and how much are you willing to pay for data. If you're logging 1,000 signals at 1 second, that's going to be a lot of data, and probably not actually going to be all that useful, because 1,000 signals is a lot of data.
And I guess if we think back to the slide where I had kind of the timeline of the system lifecycle, yeah. So up one, yeah. So the the place where you're going to be collecting super high frequency data and you basically want to get everything that happens would be, you'd be using one of our embedded data loggers or the PC data logger that basically captures everything, and that's for really fine-grained. I mean, the amount of data that can occur on a CAN bus or multiple CAN buses, if you need to collect everything, is probably, that is a case where you want to have a physical data logger with like a USB stick or a SD card. And so we offer those to assist in the earlier phases, kind of how we think about it, and that's what we were calling the testimony line. And 320 that you can put a USB stick, you can collect, like put a 16 gigabyte USB stick in there and collect, you know, at a very high frequency.
Okay, that's all the questions that have been asked so far, so let's go carry on and talk about the hardware. So this is the box that we're currently using, the C4MAX for mobile devices. It's got a 500 megahertz ARM11, so it's got a fair amount of processing power. 64 megs of RAM is pretty good. It is running Java stack, so it's not low-level C code. It's a little bit higher level than that, so it needs a little bit more room to stretch its legs. It does have 256 megs of flash. Not all of that is available for data logging, but a large chunk of it is, and that's very useful for buffering data when a vehicle is out of service, out of cell service. So it'll just buffer that on the device until it gets a cell signal back, and then it'll dump everything that it has. As I said before, this has a 3G GSM modem and an external GPS antenna. So you can sort of see here on the sticking out of the back, there are these two little colored posts. Those are the sockets for the GSM antenna and the GPS antenna. And you would stake those out somewhere near the top of the vehicle probably, so that it can get the best possible reception. In addition to CAN communications, we also have access to a serial bus, RS-232. We haven't implemented or done anything with either that or the I/O listed there. A couple of digital, a couple of analog inputs, and 2 digital outputs, but those are something that would be candidates for some custom work. Popular things for telematics control are things like locking down a vehicle if it's been determined to have been stolen. That's obviously more of a fleet management issue than an engineering development issue. And interacting with driver identification devices, things along those lines. The C4MAX box is IP54, and we have an IP65 enclosure that's available. The operating temperature listed there, -25 to +70 C. We have seen it operate at lower temperatures than -25, but the rating is at -25 because it does have an internal lithium-ion battery that does not charge colder than -25. Question comes up, how many CAN buses can this handle? It has only one CAN bus. One of our existing projects, though, has another module act as a gateway when there is data that needs to be logged on multiple buses, and that has worked quite well.
So that question probably stems from my earlier comment about the, you know, if you have the amount of data that can take place on a CAN bus or multiple CAN buses. So some of our other data loggers do have multiple CAN buses. The vCAN data logger, for instance, that has 2 CAN buses, and it's able to log that to a USB stick. So during the system development lifecycle, if you're needing to capture that high frequency and that much data, you probably want to use one of the local embedded data logger appliances to capture that data. This as an engineer, the Telematics as an engineering tool is can be useful from the onset, but in the diagram I had there on the system lifecycle timeline, I kind of had it after you'd kind of gotten past some of your development, and I've kind of been talking about it as a fleet. If you're doing fleet testing or kind of a limited beta release type, maybe 10 vehicles in the field, and you want to collect this data more than if you're kind of just standing up the initial development and that kind of thing. And even if you have a very difficult issue and you need to do some point debugging, this can be useful. But if you have to get down to the super high level of detail, that's a good case for one of the local embedded data logging appliances.
Okay, so that's the TCU, and when you buy a C4MAX from us, it comes in a kit. The C4MAX obviously is included in its kit. There's a pre-installed SIM card that can be either, we can tailor that based on where your target geography is. It can be either U.S. only, it can be U.S. and Canada. If you need a global, we can do that, although the data prices do increase the more geography you want to cover. It comes with a pigtail harness, which has a Molex 20 pin connector. We can make that a SmartCraft harness, a J1939 harness, or an OBD2 harness if you have those connectors and you just want to plug it in for some sort of on a temporary basis or on a trial for on an existing harness before you have it fully integrated into the harness itself. You also get the GSM and the GPS dual antenna you can see there on the right, and each kit comes with 12 months.
So when you get a like, let's say that you're going to get your first kit, when it comes shipped to you, how do you get it set up to run the example that we're just showing? Say you've got a model and you've got a DBC file and you want to select some of the signals from a DBC file. When the kit arrives to you, what do you have to do?
So if you've pre-ordered a pigtail harness with the correct connection, you can just plug it in, power it up, and before we ship the device, we'll provision it in the web portal that I was looking at before. So you would log into the web portal, the vehicle would be there, you would upload your DBC file, and as soon as you get the vehicle out of the garage into a place where it can get a cell connection, it'll download that update and start logging data pretty much as soon as the C4MAX powers up. Now, as I said, the C4MAX is isn't running low-level C code. It's running Java on basically on a Linux Java stack. So it does take 30 seconds to a minute to boot up and get into a state where it's established a cell connection and locked into GPS and can start processing data. It's similar to when you turn on your cell phone. It doesn't come up right away and work immediately. It's got to boot up, connect to the cell network, etc. And in terms of levels of service, we do have 2 tiers of service. Gold is CAN logging and fleet tracking, so that gets you access to both the fleet tracking web portal and the engineering web portal, and you can do either style of data logging. Platinum level, you get both of those plus remote reflash, which is what you'd use for calibration and software updates. And as a note, both of these services, we provide updates to the TCM, TCU software and settings as needed. So if there's if there's a bug that we find in the TCM software, we can fix that over the air without having to recall the vehicles. So I got a question here. since we just got to the question phase, can I please repeat how long it takes to boot up? The TCM takes anywhere from 30 seconds to a minute to boot up, and it will take the other factor is how long it takes to get a valid cell connection, and that will be dependent on where the vehicle is parked and how good the signal is there. So if you're inside of a garage with a metal roof and a bunch of electronics lying around, it might not be getting a good enough cell signal to actually make a connection. But as soon as the vehicle gets moved into a place where it's got a viable connection, it will connect and start working. And as we said before, you can tell if it's if you're having problems with connectivity. You can look at this this message, and the ID, the CAN ID we use here, is configurable. So if you have a specific ID you want that on, we can do that without any problems at all. One of these values, I think it's this value, is the cell connection, and this is the GPS number of satellites. And we can provide the specifications of that message, no problem. Are there any other questions?
So if Scott, if you're doing an application using the Platinum level and you're planning to do remote reflash, we had talked a little bit about the Safe to Update protocol. What is provided as far as guidance in implementing that in the on the ECU side? Obviously, as we discussed, you have to have it's application specific as to when it's safe to do an update of ECU, and the ECU being updated is generally making that call. So there's some software that needs to be put in a model there. What's provided as far as guidance on that?
Well, in addition to providing the Simulink library that facilitates the communication, we would be able to, obviously if we are working with you on the application, we could help figure out how that can be done safely, how the update can be done safely, what needs to be done in terms of shutting down systems that are active, making sure nothing high voltage is going to be suddenly let loose in an unknown state because we're in the middle of a reflash. Those are the sorts of things we can work with you on to help figure out how to do a remote flash safely. I'm going to wait for a couple of seconds here to let anyone else type in a question. Okay, Ben and I will hang out on the line for a few minutes in case there's any other questions you have, but other than that, that's all we have for today. Feel free to go visit our websites or give us a call if you have any further questions. Most of you have, I believe, already have contacts at New Eagle. Feel free to ping them. And yeah, we're going to do another webinar in about a month, and I believe the topic there is going to be the Motohawk Network Toolbox that allows you to use a DBC file in Motohawk instead of the M files style. So that's it for us. Thank you for attending, and we look forward to hearing from you.